Hey, Wade North, Mr. Yurgler here. Let's talk about solids and liquids. This may seem pretty elemental, stuff you've seen since probably middle school, but a quick refresher, and we're going to go a little bit more in depth, looking at specifically the IMFs that are involved in each of these phases of any given substance. Okay, so different properties of the different phases. The main thing here that I want to emphasize is that liquids, the molecules are sliding past each other, right? It's called translating. They're like translating around each other. So their IMFs are kind of holding on to each other, but not so much that they're in a rigid shape. All right, with solids, there's two different types of structures of solids. One is called amorphous, and the other is called crystalline. Amorphous is where we have relatively random arrangement of the molecules or of the particles. So you can see in here, it looks like there's some repeated patterns, but there's also a lot of randomness and disorder in it as well. As compared to something like ice has a more of a crystalline structure, the molecules form these tetrahedrons, and this is actually what makes ice less dense, because when water forms ice, it creates this ring which has actually empty space in it. These amorphous solids will tend to be slightly lower in melting points, although that's not always the case. Glass obviously has a much higher melting point than ice, but they also tend to melt a little bit differently. Amorphous solids will kind of get soft as they approach their melting point, whereas if you think about how ice melts, it's either solid or liquid. It's a very fine distinction. Examples of amorphous solids would be like butter or plastics or rubber. A lot of synthetic, a lot of polymers are amorphous solids. They tend to soften before they melt. All right, this solid to liquid transition, I want to think of it in the context of water. Water has hydrogen bonding as a solid, and it still has hydrogen bonding as a liquid because the type of IMF is dependent on the substance, not the phase that it's in. There's energy required to break the IMF bonds, right? So in ice, these molecules are vibrating. They still have kinetic energy, but not so much that the IMFs are broken, and so they form this rigid shape. As we increase the temperature, you can think of temperature as the amount of motion of the molecules. As we increase that motion, eventually the motion gets too much for the IMFs to hold on, and so they'll begin to break. And so in a liquid, they've broken, but they're kind of reforming as well because they're not completely a gaseous phase, and that's what allows them to translate, to move around each other. Here's a heating and cooling curve. So on the x-axis, heat is being absorbed over time, and we're tracking the temperature on the y-axis. If you picture an ice cube that you take out of the freezer, it's probably below zero. And so it would first have to heat up to zero. It won't start melting until it gets to zero. Once it gets to zero, if we track the temperature over time as it absorbs heat from the room, the temperature actually flattens out. It stops increasing. But it's still absorbing energy because there's still heat transfer. That energy is being used to break these IMF bonds. So here we have water at 0 degrees, and at this point we have ice at 0 degrees. Once it's completely melted and it continues to absorb heat, then and only then does it start increasing in temperature up until it gets to the boiling point. In liquids, the IMFs are responsible for a lot of the properties of liquids. One being viscosity, the amount of translation of the molecules. This is obviously related to temperature as well. A liquid that is very low in viscosity, the molecules are able to move past each other relatively easily. When you think of something with a really high viscosity, it resists flow, and so the molecules, it's almost a solid, right? The molecules are holding on to each other, but not so much that they have a rigid shape, but almost. It also affects capillary action. Water is polar, glass is also polar, and so they attract each other, which is what brings water up, kind of climbs up the walls of a glass tube. Mercury, on the other hand, will form a convex meniscus because it's not attracted to the glass. It's more attracted to itself than the glass. This also affects surface tension. So if we think about these water molecules in like a droplet of water, the interior molecules are pulled in all directions, but the ones at the surface are only pulled in a couple directions. They're pulled downwards, but they're also pulled sideways. And this almost kind of creates like a fabric or like a film of molecules that are held together because they're not pulled upwards. They're only pulled downwards and sideways. And they're kind of linking up to create that surface tension. The greater the IMF, the greater the surface tension. The last thing is melting point and boiling point, right? This is the heating curve for water. We could also have the heating curve for something else like wax, where it might melt somewhere around 60 or 70 degrees Celsius. So your melting plateau wouldn't be at 0, it would be up here. The higher the IMFs, the higher the melting point, and then therefore the higher the boiling point as well. I like using this simulation because it kind of shows what's happening as something transitions from one phase to another. This is argon, so this would be a nonpolar atom. So we'd have London dispersion forces. Notice that the temperature is really, really low when I choose solid. We need to have very low amounts of energy because the molecules are not very strongly attracted to each other. As we heat this up, as we increase the vibration, eventually the molecules, or the atoms in this case, are able to kind of slide past each other, so that would be like a liquid phase. And this model isn't perfect. It doesn't really show them flowing to the bottom. It kind of seems like it's kind of in a low gravity environment. Once we increase the temperature even more, increase the motion of the particles, eventually they have enough energy to overcome their IMFs, which in this case is still going to be below zero because it's argon. It's a gas at room temperature. Water as a solid is going to have a rigid structure, so the molecules are not sliding past each other. They're kind of locked. They don't have enough energy to break their IMFs. Once we increase their temperature, eventually they start sliding past each other. They're kind of grabbing each other and then letting go, right? And grabbing someone else and letting go. And so they slide past each other. A few of them can even break off potentially and evaporate.